Hey, this is Ankit, and I'll be answering question number 6 on the biostat midterm. And the question is, using diastolic blood pressure as the outcome, build a regression model with daily smoking as the predictor. Does the model improve by including age, BMI, or total cholesterol? Does the inclusion of any of these predictors change the association between diastolic blood pressure and daily smoking? If so, how and how much? What would be the best model? Why? Make sure to check the assumptions. Okay, so before we actually continue, we should clarify what improving the model means. And so that means, does the model become more fit as we start adding more predictors in? And that table can be summed up by the model summary table, which we'll see later in our regression. Um, does the inclusion of any of these predictors change the association? Is just another way of saying, does the slope change for cigarettes, and how much does it change? Um, when we look at the change, it may not be good, or it may be good in a different way, and you'll see what I mean there. So let's get started and do a regression for just daily smoking and diastolic blood pressure to see how well it predicts originally. So we go to regression, linear. Let's reset everything. And we're going to put diastolic blood pressure into our dependent variable box and daily smoking into our independent variable box. We're going to check off some statistics. We want confidence intervals to see where our true data lies between a lower bound and an upper bound. A Durbin-Watson test to see whether our errors of our residuals are independent, and case-wise diagnostics to see if our outliers are, if there are any outlier values. Collinearity diagnostics are useful when we have two or more independent variables, and we will be checking that off later, but for now we won't. Go to plots. We're going to we want to check out for homoscedasticity and normality of our residuals, and the way to do that is to put standardized residuals into our Y box and our standardized predictors into our X box. We can check off histogram and pp-plot to see whether these residuals are normal or not. We can check off these values if you want to see any influential cases. I'm not going to do it because it does a messy job of dumping the values and saving the values into the spreadsheet, and because I'm going to be using the spreadsheet later to explain another question, I don't want to do that, and mainly because I'm lazy. But normally it's in good habit to do this, but I'm not going to do it. Okay, I think we have everything checked off, so I'll hit OK. Okay, so right here we can see our model summary, and what this tells us is how well the predictor predicts the outcome, which is diastolic blood pressure. And as you can see, the association is really weak. It's 0.042. That's not a good association, and what even more important, the interpretation of the variability accounted for in diastolic blood pressure by number of cigarettes smoked is also not very good. This is less than 1% or 0.02 of a percent. So less than 1% of the variability in diastolic blood pressure is accounted for by cigarette smoking. That's not very good. So hopefully when we include more independent variables, our model becomes more fit and better at explaining our outcome. We can see that the errors in our residuals are independent of each other by the Durbin-Watson value of 2. Can go further down here, and we can see that our slope for cigarettes per day is negative 0.041. So another way to interpret this is as we smoke 1 cigarette per day, our diastolic blood pressure decreases by 0.041 millimeters of mercury. Now that doesn't seem to make sense, but we can maybe start adding predictors in here to see if that slope changes, see if we can control for confounding, which is exactly what including these predictors are for, to see if there are better predictors to explain the variability or explain the outcome in diastolic blood pressure. Another thing to notice is cigarettes per day did occur by chance. It's not under the magic p-value of 0.05, which means that there's a 34% chance that this occurred in a null world. So this raises a red flag on whether cigarettes per day is actually associated with diastolic blood pressure, or even does anything to explain diastolic blood pressure. It may or may not, and that's what including more variables will help tell us. We can see that our residuals are fairly normal from the sort of normalish curve. Our PP plot also tells us a similar thing, that most of our data points follow a line. And, well, these this probably is not homoscedastic, because these data points are so spread out going to the far right. So we probably can't check off for homoscedasticity for this data point, but that's okay. Let's go back and see if adding a variable changes anything. Go back to analyze, regression, linear. We'll do age. Everything's the same. Okay. Oh, I forgot something. I forgot a very important thing, which is checking for multicollinearity. Multicollinearity just tells us whether two independent variables are highly correlated with each other, and if they are, that means their errors are dependent of each other, and that causes problems. We'll do that again. Okay. So we can see here that our model has become slightly more fit, not really by much. There is a slight improvement from 0.02% of variability accounted for to 0.005% of variability accounted for by diastolic blood pressure. So we can probably infer that age isn't that great of a predictor either when put into the model. So our errors are independent of each other, and if we go down further to here, we can see that our slope didn't really change much for cigarettes when age was included. We can also see that our significance value also increased. So now we're more certain that cigarettes has occurred by chance. So we're more certain that that cigarettes has no association with blood pressure. We're not 100% certain. We're only about 52.8% certain that cigarettes is not associated with diastolic blood pressure. But we can also see that age also has occurred by chance. This is going to tell us that maybe age doesn't have a lot to do with the outcome either. So we can safely say that maybe cigarettes and age are not good predictors of diastolic blood pressure. We can see that they're not highly correlated with each other. You can see that the residuals are pretty normal, as shown by the PP plot, and that this graph is much more homoscedastic. Can't say the word. And so our assumptions are checked off. So let's check another independent variable out and see if our model gets any better. Back to regression. Take out age and we'll throw in BMI. Hit OK. Okay, so by looking at our model summary now, we can see that BMI actually does a much better job at explaining diastolic blood pressure. We can see here that there is a weak association of 0.317, but at least there's about 10% variability explaining diastolic blood pressure by BMI and smoking cigarettes. So even though this is only 10% of the variation explained, meaning there's 90% unexplained, it's still something. We can see that the errors are independent of each other, so the residuals are independent of each other. Looking down here, we can see that the slope has changed quite a bit from negative 0.041 to 0.042. That's almost about a 0.05 difference in the positive direction. So there is a significant difference when BMI is added. So we can say that BMI could have been a confounder in this model because it explains diastolic blood pressure much better than cigarettes. Not saying that there was an association between cigarettes per day in the first place, but assuming that there was, BMI would be the confounder because it does explain the variability in diastolic blood pressure. And we can see that by the slope change. Another way to interpret this, I'll be interpreting BMI, is that as your BMI increases by 1 unit, and the unit is right here, your diastolic blood pressure also increases by 0.888 units, or millimeters per mercury. We can see that it did not occur by chance, but we can also see that cigarettes per day, the model, has also increased in the p-value, which means that we're becoming more certain that cigarettes per day has occurred by chance. So we're 77.7% sure that there's no association between cigarettes per day and diastolic blood pressure. And so this is what I mean by how the model changes by the inclusion of predictors. We can see what a good predictor is and a bad predictor is by just putting them in and seeing how well the model predicts the data. And right now it's not doing a good job at predicting cigarettes per day. We can also see that both cigarettes per day and BMI do not highly correlate with each other, which is good. The distribution seems pretty normal. The histogram is normal. The PP plot seems to be normal, and the data seems to be pretty homoscedastic. I mean, most of the data points lie clumped up with each other. They're not spread out too much. So we can be sure that we can be pretty sure that BMI is good at explaining variability, at least 10% of the variability in diastolic blood pressure. There's one more variable that we need to check now, which is cholesterol. And then we'll start putting in 2 variables at a time. Okay. So cholesterol, just at first glance, it seems that it does not do as good of a job as BMI did for predicting the outcome for predicting the outcome, but at least it's doing something here. Only about 3% of the variability in diastolic blood pressure is accounted for by total cholesterol. It's not much, but it is something. And we can see here that cigarettes per day did not change much in slope, and it is still insignificant. So by putting these additional predictors in, we can see that cigarettes per day is not doing a good job at predicting diastolic blood pressure. We almost want to take it out. And the next model that I'm about to do with total cholesterol and BMI will confirm that cigarettes per day is not a good variable to use to predict the outcome. We can see that by the collinearity value VIF, that total cholesterol and cigarettes are not highly correlated. As we can see, the residuals seem normal, and this looks homoscedastic to me. Okay, so the last thing we're going to do is find our best model. Now I know this is our best model because I've already done this, and I've already put it in the appendix of my midterm. So if you want more information, you can just look at the data in the appendix, but I'm just going to skip right to the best model and why it's the best model. Okay. So now we have BMI and total cholesterol along with daily smoking predicting for diastolic blood pressure. Okay, So here we can see with these three variables that our association is much larger. Not much larger than BMI alone, but it's still um, more highly associated. Um, the R squared is now 12%. So we can say that 12% of the variability in diastolic blood pressure can be accounted for smoking, serum cholesterol, and BMI. We can see that our Durbin-Watson value is 2, so there is independence of residual errors. Okay. The first value that I want to pay attention to is the slope of cigarettes. This is 0.001 and with a significance value of 0.986. So what this is telling me is that we'll round it up, we're 99% sure this has occurred by chance. That cigarettes occurred in a null world. In other words, there's almost no, it's very, very likely, we're 99% sure that there is no association between cigarettes and diastolic blood pressure. And we can see this also by the slope, that as you smoke 1 cigarette per day, your diastolic blood pressure goes up 1,000th of millimeters of mercury. This is almost close to 0, so there's almost no association between the number of cigarettes you smoke per day and diastolic blood pressure. And we can use the slope, the significance value, and as well as the confidence interval to show that it captures the no association criteria. And we wouldn't have known that without serum cholesterol and body mass index confounding for that, or controlled for confounding because of that. So now we're pretty sure that cigarettes is not associated with the outcome, and that cholesterol and BMI account for 12% of that. And we can go back and check. We'll take smoking out and take a look at it. Yeah. So you can see here that the variability has not changed much, and the adjusted R squared has not changed much. So we can be sure that smoking doesn't really affect the data that much. It's not associated with diastolic blood pressure at all, so there's no reason to put it in there. We can see here that both total cholesterol and BMI has not occurred by chance. We can interpret these values as 1 unit of BMI increases, your diastolic blood pressure will also increase by 0.837 millimeters of mercury, as well as total cholesterol increasing by 0.037 milligrams per deciliter as 1 milligrams per deciliter increases, your diastolic blood pressure will increase by 0.037 millimeters of mercury. You can see here that none of the predictors are highly correlated with each other according to the VIF value. Our residuals are normal. And the data seems to look homoscedastic with the exception of a few outlier variables. Okay. I think that's it. I've checked the assumptions for all of my models. I've explained why this model is the best by running the model with and without the cigarettes per day. You can even take a look at the slopes to see how much they've changed. Yeah, so not all that much in comparison to the other model. And these tables explain how well our model improves by inclusion of certain predictors, and this table tells us how the association between the predictors are weak or strong, and we can definitely use these two predictors and explaining why this predictor is a very weak predictor in explaining diastolic blood pressure. Okay, hopefully that answers the question and I get full credit for it. Thank you very much.